Justin, just to confirm, no class on Monday for Labor Day?
That's on the. Just want to remind you guys that they don't either.
But I'll definitely come.
Not sure, but I think there's also Fridays. So I need to check.
Isn't it in November? Thanksgiving?
Something else. That's, I always check and tell you guys in class. Please do not come. So I'm still 30. And you guys started reading chapter 2. That's the first section. We're starting to look at performance. Want to answer these questions in this chapter. What is performance? What are the different performance metrics that we use? And how are we going to use those metrics to evaluate performance? And towards the end, we'll also look at power trends and if we can on pitfalls. Get through most of this. And just as homework 1 will likely be posted sometime Monday. We'll have at least a week to work on it. But homework 1 will be focused on chapter 2. Because chapter 1 is more of a introduction to topics. Chapter 2 is the first content. Alright. So we already got through this from the last lecture. So let's get to where we looking at anything. So we didn't talk about this too much, but I did just want to mention that for our performance, in terms of time, what we are concerned with is strictly CPU time. So the time that the program is actually running on the CPU. So this CPU time does not count the stalling cycles, waiting for inputs or outputs. Like if your program has a prompt and it just waits for you to type an answer, right? It's waiting for your keyboard inputs. And also if it gets interrupted by something like the mouse movement. So it's not running on the processor for 100% of the time. And then it's going to be broken into these 2 different pieces. So system CPU time. So this is the CPU time spent in the operating system. So that's when it gets interrupted by the scheduler saying, oh, we're a system that needs to run multiple programs at once, right? Because in order for me to do something like this, and say I only had 1 core, the only reason that we can do this is because the CPU can swap tasks very fast, right? And then it's the user CPU time, which is the CPU time spent in the program, which is the CPU time that we're concerned with. We're going to use this time to compare performance across different CPUs with the same program, usually. So again, our focus, user CPU time. Okay. So we talked about response time. So this is just how long does it take to do a given task, okay? And then we talked about throughput, which is how many things can I do in some fixed unit time. And then CPU time is our performance metric. Okay. So one thing that we should define is the word performance. So with CPU time, smaller is better, right? But when we typically think about the word performance, we want larger is better, right? So we're just defining performance as the reciprocal of the CPU time. Because now, if CPU time goes down, performance goes up, right? CPU time goes up, performance goes down. And then if we want to compare the performance of a program on two different processors, we're going to take the performance of the two and take the ratio. And in order for this statement to be true, like CPU time on Y is n times as long as it is on X, Y should be the one that is larger. Okay. So whenever you're comparing two things and you're trying to figure out the speed up, you take the one that is larger in terms of execution time, divided by the one that is smaller in terms of execution time, and you get that ratio. But if you're talking about performance, you have the performance of the higher number divided by performance of lower number. Right? And once you have this ratio, you would say the CPU time Y is n, which is this ratio, times as long as it is on X, or n times as fast. So this is one of the mistakes that a lot of people make on like the exam. So a lot of people would forget about this equation and this standard. And maybe you find the ratio and it comes out to 1.2. And then some students would put it is 20% faster. So it's not wrong, but it's not the standard that is used. Okay. Okay, so here's a speed up example. So computer A runs a program in 10 seconds, computer B runs a program in 15 seconds. Which computer is faster and by how much? So we know 15 is larger than 10, so computer A is definitely faster. And then we take the slower time, which is computer B, 15 seconds divided by the faster time, computer A. The ratio is 1.5, so we say computer A is 1.5 times faster than computer B for this given program. This may not be true across all programs, right? So another key performance metric is the clock rate of the CPU. Right? So the operation of the digital logic in the CPU, the speed of it is limited by the clock rate, right? So the clock rate is this wave. It's a square wave. Usually it's 50% high, 50% low, and the logic cannot move forward until the next clock. And usually we define the beginning of the clock as the positive edge here. Positive edge because it's going up. This would be the negative edge. And then here's the next positive edge. So this is the clock period, right? And then the clock rate is just 1 over the period. So cycle time is period. So this is the frequency, that's the clock rate. And here we can see the data transfer and computation. And this is when it gets updated, and then here we can do more data transfer and computation. And here's your example, so cycle time, if it is 250 picoseconds, which is 250 times 10 to the negative 12 seconds, right? The frequency would be 4 gigahertz. Or 4 times 10 to the 9 hertz. Which, and this is just 1 over 250 times 10 to the negative 12. So we're all good with this? Convert between the two? The other common mistake is forgetting these conversions. Because we are going to be dealing with like nanoseconds, milliseconds, things like that. You have to know the appropriate conversion. Sometimes students would forget to convert them to the same scale. Okay. Okay, so here is checkpoint number 1. There's just so let me get your code. Your code is 702. Answer this on your own first.
We have to use like 490 as our response.
Yes.
Do not realize that it always resets each time, so we get the him.
If you make any shun odyssey. Oh, you don't have to. And it shows up on here. Just yeah, I think we are mostly done thinking about this on our own. So do talk to the people around you. We are not at threshold. We are not near the threshold. As I think.
Right.
Sure.
So I see that it has a faster processor on the top, but how many cores is there? Like, it's so many of those things. I didn't think that it has two pretty fun. I'm not 100% sure that there could be, there's other factors that do, but the speed on a computer.
Yeah, I guess there's like laptop on this side.
Right, but that's, I could be convinced
So what do you do? And then, because I was thinking the stuff where it comes to like increase. So what makes it for sure? Right. Okay.
If you were convinced to change your answer, do change your answer. You had some movements, but not a whole lot of movements. So, does anyone want to advocate for A?
It's because it's a greater number, that means you were dividing by a smaller clock rate.
Uh-huh.
So I was thinking, just based on that fact alone, then it'd be for sure faster.
Okay, anyone want to advocate for B? I would imagine no one. No one answered B. Okay, what about C? Uh-huh,
It doesn't take into account like instructions per clock,
yes,
so it's not the full story.
yes. So this is just one performance metric that is part of our performance equation. So although it could be an indicator, it does not mean we are for sure faster. So another factor for this is not just the microarchitecture itself. What else could be the factor?
Like how many cores it has, how many jobs it can perform.
Yeah, so that is also microarchitecture. Okay. But it's a different kind of thing, and because of those things, the instruction per clock would be potentially higher. But what about something that's not microarchitecture?
Would the memory speed matter at all in that regard, or is that considered separate?
That would matter. Sure, we can talk about that. Because if your memory is faster, you're going to stall less when you need to wait for a memory. But it's something that we talked about with the ISAs. Are all the ISAs the same? And some ISAs are more complex, okay? More complex instructions. And some ISAs are simpler, right? With very simple instructions. So if you have to implement more complex instructions, you're able to do more per instruction, right? Like for x86, there's an instruction where you can, in one instruction, do a matrix multiplication. So that is a very complex instruction. And what do we know from digital logic? More complex,
Longer time.
longer time means slower clock rate, right? So it could be a slower clock rate, but it could be getting more done. But again, going back to digital logic, if I have this instruction that my microarchitecture needs to implement, but the program never uses it, then I still have that clock rate, right? It's still longer. So the ISA itself could also be a factor in how many instructions is needed to do this task. Make sense? So the key point from this slide is you need to think about all of the different factors that go into the performance equation. And then you can calculate whether something is faster or not. Okay. So this is the beginnings of our performance equation. So we have CPU time, our user CPU time, right? And we have the number of clock cycles and the cycle time. So basically, how long is a cycle, right? And then how many of those cycles do we have to wait in order for the program to finish, right? And then if we convert cycle time to clock rate, this is just clock cycles divided by clock rate. So we have, right now, we have two pieces to our performance equation. How many clock cycles? And what is the clock time, cycle time? And we will expand the cycle time in Wednesday's lecture.
About Monday.
There's no lecture on Monday. It's
Labor Day. Yes.
okay, so, but from this, we can improve performance by doing what? How can we improve performance from this equation?
More simple instructions.
And what could that lead to?
With cycle time.
Yes, less cycle time, but what else would have to happen if we have more simple instructions? Most likely, we would increase the number of instructions. And if we increase the number of instructions, most likely we increase the number of clock cycles. But if the ratio is lower, then it still would be worth it. Okay? So, but there are two different things that we can target, right? We can either try and target lowering the total number of clock cycles and potentially maybe without impacting cycle time. Or we can try and lower the cycle time, also trying potentially to not impact the number of clock cycles. So performance is improved by doing what to the number of required cycles for a program? We want to decrease it, okay? And for cycle time, we want to decrease it. But for clock rate, we want to increase. Yeah. And like we just talked about with your suggestion of making simpler instructions, the hardware designer must often trade off clock rate against cycle time, as they are kind of opposing forces. Usually when you affect one, you're going to affect the other in some way. Okay, so CPU time example. So a program runs in 10 seconds on computer A, and it has a 2 gigahertz clock. And we are trying to help a computer designer build a new computer B that will run this program in 6 seconds. The designer has determined that a substantial increase in clock rate is possible, but this will affect the rest of the CPU design, causing computer B to require 1.2 times as many clock cycles as computer A for this program. So the question is, what clock rate should we tell the designer to target in order to achieve this 6 seconds of execution time? So here's basically our information first, right? So the clock rate of computer A we know is 2 gigahertz, right? And we also know that its CPU time is 10 seconds. So we have an equation with 3 variables, and we know 2 of them. So we can solve for the third, right? So what can we solve for here?
Use clock rate.
Not computer B. Computer A's
Clock cycles.
clock cycles. Yes. And here's the other information we have. So we know that the CPU time that we want to accomplish is 6 seconds. And then the clock cycles for computer B is 1.2 times the clock cycles of computer A. Right? So we're going to first use this information to solve for clock cycles A, right? And here's your hint, right? Use this equation that we just went over. And we talked about how to get started, and then you can finish with the same equation for computer B, right?
So there's clock rate, clock cycle, and what was the last one?
So clock rate and clock cycles are reciprocals of each other, right? But your performance equation is CPU time is equal to the clock cycles times the cycle time.
Okay.
But cycle time and clock rates are really the same thing. It's just a reciprocal of each other. So again, work on this on your own. Is anyone still thinking about this? Right, so we are close to the threshold, but we can use this time to your discussion. So go over how you got to your answer with the people around you. See if there's anything different, and if you're convinced to change things, we can change things.
Oh my God.
The race of just like. So 10 seconds, clock like play. Saying it's like from the beginning. And figure out what that's clock is. And then you fill in the next one. So like 6 seconds equals. When you play blocks are being, and then you want to find.
We're putting it into the option first. So we have the CP and we have the CP separate. In terms of CC, so. Super different. We need to put this.
First, because it's personal views, clock cycles, divided by usual time. Let's see, time for V is 6 seconds.
CCB was. The CPU time is.
And if you were convinced to change it, so do change your answer. Okay. Like you guys are moving towards the right direction.
Right.
Okay, so let's do this together. So I'm going to put all of this up here first, and then we can walk through it. So as we discussed, we have our performance equation for A, right? And we know the CPU time and we know the clock rates, right? We know these two things. So we can solve for the clock cycles. So we multiply those two and we get 20 times 10 to the 9 clock cycles. Okay? So 20 billion clock cycles. And then here we have the same performance equation, but for B, and we're just rearranging it because we know we want to solve for the clock rate. And then we need to figure out the clock cycles for B. We know that it's related to clock cycles of A by 1.2 times. We just solved for clock cycles of A, okay? So we plug that in here, and then CPU time, we know we're targeting 6 seconds. So once we have it all, we have 1.2 times 20 times 10 to the 9 divided by 6. So 24 times 10 to the 9 divided by 6. 24 divided by 6 is 4. And then 10 to the 9 gives us gigahertz. So we are 4 gigahertz. So your answer is C. So we all see how to do this? So just as a recap, performance is the reciprocal of CPU time. And the reasoning for this is, why do we do this?
CPU time is a small number, but we want to measure performance with a bigger, I guess.
Yeah.
I mean,
That's really the only reason that we're defining performance this way. Because usually when we're talking about performance, we want higher number, right? Higher number better. But if you talk about strictly CPU time. And then if we want to compare two different processors, we're going to take the reciprocal, well, the ratio of the performances, or you can equivalently take the ratio of their CPU times. And then our CPU time equation for now is the number of clock cycles times the cycle time. And we also know that cycle time is 1 over clock rate. So we can substitute clock rate in for cycle time. So this is our performance equation. And on Wednesday, we will talk more about expanding this equation to solve for the number of clock cycles. So the number of clock cycles is going to be split up into two new variables: instruction count and cycles per instruction. And if you think about it, if I know how many instructions there are, and I know how many cycles it takes per instruction, multiply those two, what do you get? The total number of clock cycles, right? So how does the total number of clock cycles relate to the number of high-level instructions in the program? So is it the same as the number of C++ instructions?
yes.
So when you write C++ code, right, it gets translated by the compiler into machine, like the assembly code, right? And if you look at the number of lines in C code to the number of lines of assembly code, do we have an increase or the same?
It's increasing.
Yeah, so it's an increase. So we're going to see this increase. So does the number of clock cycles depend on the type of instructions executing? Yes. Okay. Because you could have, say, floating point instructions, right? So a floating point instruction might take multiple cycles, whereas a fixed points instruction may take just one cycle. And then the other thing that can happen is if you're a load or a store, right, that's accessing memory. Memory is on the order of 100 to 150 times slower than the CPU. So if you miss in the cache, right, and it's not there, then you have to wait for memory. So your memory instruction might take 150 clock cycles. Okay. And the other thing is multiplication, addition, but we also use the floating point example. Okay. So there's floating point versus integer. And then that's our memory access. Right, so we can do a little bit early today. You do have another reboot. This is for Wednesday. And I believe there is also a reading for Friday. And both of those should be posted. And the quizzes are available already. So if you want to knock them all out before Wednesday, in the 3-day weekend, you can do it.
Thank you.
Labor Day.